All right, welcome back. So in this video, we'll be looking at the exponential function, which is denoted by exp, and we'll be looking at the properties of this exponential function. So in particular, this is known as the natural exponential function. So what is this? The exp of x is basically the inverse of the natural log function ln of x, which we developed in detail in the last few videos. So because exp of x is the inverse, so then the domain of the domain of the exponential function is the same as the range of the natural log function, which is the entire set of real numbers, and the range of the exponential function would be the domain of the log function, which is from 0 to infinity. So because the exp of x, exp is the inverse of the natural log, so the exponential function applied to x gives us y if and only if the log function applied to y gives us x. So in other words, the exp of x is equal to y if and only if x is ln of y. And because exp of x and ln of x, they are inverses, we have the cancellation properties. That is, if we take the composition of exp and ln, then we just get the identity function x. That is the composition of the exponential and the natural log function takes the input x to the output x. So we get the identity function when we take the composition of these two functions in any order. So in the first case, because we are ln of x is ln, the natural log is the inside function, so that then the domain of this composition would be the same as the domain of the logarithm function. In the second equation, because the inside function is the exponential function, then the domain would be the domain of the composition would be the domain of the exponential function, which is from negative infinity to infinity. So the first equation is true for all positive x, and the second equation is true for all real numbers x. Well, recall that ln of 1 is 0, and therefore e to the exponential function evaluated at 0 would be 1. And because ln of e is 1, in fact, this was the equation that defines the number e. So ln of e is 1, and so the exponential function evaluated at 1 would be e. Okay, so that's the exponential function, and let's look at its graph. Recall the graph of the natural log function. So the green curve here, that's the graph of the natural log function, and this is the line with slope 1 passing through the origin. And so the red curve is the graph of the exponential function, and because the exponential function is the inverse of the natural log, the graph of the exponential function would be the mirror image or reflection of the graph of the log function across the line y is equal to x. Now notice two things from these graphs. One of them is that recall that the ln of x approaches negative infinity as x approaches 0 from the right. So as x goes to 0 from the right, the log function is decreasing without bound. In other words, the y-axis here is a vertical asymptote for the log function. Now exp of x being the inverse, notice that it has a horizontal asymptote, which is the x-axis. So because of this because of this limit right here, then because exp of x is the inverse of the log, we can do the opposite here. That is, as x goes to negative infinity, exp of x goes to 0. So as x goes to negative infinity, exp of x goes to 0, and which is what we are getting from this equation. Another fact is as the limit of ln of x as x goes to infinity is infinity, and as a result, the limit of exp of x as x goes to infinity will also be infinity. So in these two equations, why do they work? Well, the reason is, if we think of, ln of x as y, so what we are saying is that okay, so let me write that here. So let's say ln of x is equal to y. Well, then we know it means that exp of y would be x. So this limit right here, so what we are seeing here is that as x goes to 0 from the right, we see that ln of x goes to negative infinity, which is, we're denoting by y, so y goes to negative infinity, right? So therefore, and because they are inverses of each other, so notice that as y goes to as y goes to negative infinity, exp of y is going to 0 from the right. Okay, so that explains. So that shows that this limit implies this limit right here, and similarly the other one. Okay, so I'm going to pause here for a second, and I'll be back after I take a breath. All right. So let's recall the way we defined the number e. So we said e is the real number such that e is the positive real number such that ln of e is 1, right? This is the equation that defines the number e. So let's let n be a positive integer. So I assume most of you know that e to the power 0 is defined to be the number 1. E to the 1 is the number e. E to the 2 is the product of e with itself. And more generally, e to the power n is basically the product of n factors of e. So in other words, this is the same as e to the e times e to the n minus 1 for any n bigger than or equal to 1. So this is the for n greater than or equal to 1. Now, what is the meaning of? So we understand, when n is a positive integer, we understand what it means to raise e to the exponent n. The question now is, what does it mean to raise e to negative n? So n is a positive integer, so negative n is a negative integer. What does that mean? Well, it simply means 1 over e to the n. So in particular, e to the negative 1 means 1 divided by e. And we can think of e to the negative n in a little bit differently, like this. So it is 1 over e to the power n. Now n is a positive integer, so it is the same as, it means 1 over e times 1 over e. So we multiply n factors of 1 over e. Okay, so that's what it means to raise e to a negative integer. Okay, so now I want to come to the meaning of raising e to a rational exponent. So first of all, let's look at what does it mean to raise e to 1 over n. Remember, n is a positive integer. So, well, it means the following. It is the e to the 1 over n is the positive real solution of the equation x to the n minus e is equal to 0. And this is not the graph of this. This is not the graph of this function f here. I'm just saying that when you have a real solution, real root of this function, it means the point on the x-axis where the graph of f crosses the x-axis. So this is the x-intercept. So we're talking about the x-intercept of the function f here, which is x to the n minus e. So the real positive solution of this equation x to the n minus e equals to 0, well, that equation is the same as x to the n is equal to e. So we're saying e to the 1 over n represents the positive real solution of this equation, and we can, we know that there is a positive real solution of this equation because this function f has both a positive and a negative value, and it is a continuous function. Therefore, it also takes on the value 0 somewhere. Okay, so now that we understand what it means to raise e to a rational number of the form 1 over n, let's see what it means to raise e to a positive rational number. So let's say m is also a positive real number, positive integer. Then e to the power m over n simply means e to the power 1 over n to the power m. So that is, we multiply m factors of e to the 1 over n, and we already know what it means. So another way, we say that e to the 1 over n is the nth root of e. So we are multiplying nth root of e m times right here. Finally, what if I have a negative rational number? Well, that's easy. E to the negative minus m over n is equal to 1 divided by e to the m over n, and we already have a meaning for the denominator here from this equation. So far we understand what it means to raise the number e to a rational exponent r. So if you have a rational exponent r, we understand what e to the r represents. The question then is, how do we define e to the power a irrational number, an irrational number? Okay, so that's what we're going to explore now. So e to the r is actually we're now going to explore the connection between e to the r and the exponential function exp of r for any rational number r, and I'm going to show that they are the same. So e to the r, again, remember we just defined e to the r for any rational number in our discussion right here, and I'm going to show you that now that e to the r has the same value as the exponential function evaluated at r when r is a rational number. So let's say r is a rational number, then ln of e to the r, well, using the rule number 3 for the logarithm function, we know that this is equal to r times ln of e, and ln of e is 1, so we get r, and we also know that ln of the exponential function evaluated at r is also r, because ln and exp, they are inverses, so their composition is going to give me, will take r to r. So in other words, ln of e to the r is the same as ln of exp of r when r is a rational number. So remember rule number 3, previously when we stated that for only rational exponents. So because ln is a one-to-one function, then these two inputs are the same. So e to the r and exp of r are equal. So what we have just obtained then is that when r is an irrational number, when r is a rational number, e to the r and exp of r are the same. Now we know that exp is defined for any real number. So exp is also defined. So exp is defined for any real input. So now we can define e to the power any irrational number to be the value of the exponential at that irrational number. So that is, e to the x is defined to be exp of x for any irrational number x, and therefore in general for any real x, e to the x is equal to exp of x. Okay, so I hope you understand the discussion here is that, you know, I was trying to give a meaning to, you know, what does it mean to raise e to any irrational exponent or rational exponent. Okay, so now that we are going to denote exp of x by e to the x as well. So the cancellation property exp of ln of x is equal to x, this equation can be rewritten as e to the power ln of x is equal to x. So this left hand side is the same as this right here. And ln of exp of x is equal to x. That is another cancellation property because ln and exp are inverses. This can be rewritten as ln of e to the power x is equal to x. So now, you know, we are going to be using these two formulas right here. Okay, let's do some examples. All right, so ln of x is 5. And so we know that because of the exp of x is the inverse of that, right? So then we know that e to the power 5 would be x, right? So and another way of getting there is that we can raise e to both sides. So we can do e to the power 5 and e to the power ln of x. And if these two are equal, then these two are equal because the exponential is a one-to-one function. But e to the power ln of x, we just stated that e to the power ln of x is the same as x. So here we're getting x, and that's equal to e to the 5. Even though we don't really need these two steps here, we can go from here to here directly just by the fact that the e to the x is the inverse of the ln function. Okay, let's solve e to the power 5 minus 3x is equal to 10 for x. How do we solve that? Well, we're going to apply ln on both sides. So we take ln of e to the 5 minus 3x is equal to ln of 10. And we just looked at this equation here. Ln of e to the power something is equal to that exponent. So we're going to get that 5 minus 3x here, and then ln of 10. And then now we solve for x. So minus 3x would be ln of 10 minus 5, and then x would be, we are dividing by negative 3. So as I was dividing by negative 3, I noticed that I wrote the right hand side as 5 minus ln of 10. In other words, what I should have said is from this line we get x is ln of 10 minus 5 divided by negative 3, which can be rewritten as 5 minus ln of 10 over 3. All right, so the next thing I want to do is look at derive the derivative of the exponential function. All right, so how do I derive the derivative of the exponential function? So I'm going to show you two ways. First of all, let's recall that the derivative of the inverse of f, evaluated at x is the same as 1 divided by the derivative of f evaluated at f inverse of x, which I'm going to rewrite as 1 divided by f prime of y, and then y would be replaced with f inverse of x. So in other words, what I'm saying is that in order to find the derivative of the inverse of f at x, we first find 1 over the derivative of f, and then we replace the input by f inverse of x. So that's what I'm going to do here. So we want to find the derivative of e to the x, and ln of x is the inverse of that. So so think of f inverse being e to the x, and then f would be ln, right? So if I take f inverse to be the exponential function, then f would be the log function. So to find the derivative of e to the x, well, that's the same as the derivative of exp of x, and it's the inverse of ln. So we take 1 over the derivative of the inverse of exp, which is ln of y, and then once we take the derivative, we will plug in exp of x for y. And so this is, we know that the derivative of ln of y is 1 over y. So now we plug in exp of x in place of y. So we get this 1 over exp of x, and that is exp of x, which is e to the x. So what we are obtaining then is that the derivative of e to the x is equal to e to the x. So the derivative of this function is the same as itself. That is, the rate of this function is itself. The rate of the function equals the function here. Now, here is another way of deriving the derivative of the exponential function. So derivative of the exponential function I'm going to derive this by using the implicit differentiation. So the way it works is that I'm going to set y to e to the x, and then ln of y then would be equal to x. Okay, now we take the derivative of both sides with respect to x. So derivative of ln of y with respect to x is equal to derivative of x. Now derivative of x is just 1. Now derivative of ln of y with respect to x would be 1 over y times y prime. And so y prime is equal to y. But again, what is y prime? Notice that y prime simply means the derivative of e to the x, and y simply means e to the x. So we are getting the derivative of e to the x is e to the x. Okay, so the derivative of the exponential function is itself. All right, so the laws of exponents, you guys are probably familiar with this. So e to the power x plus y is e to the x times e to the y. E to the x minus y is e to the x divided by e to the y. E to the x to the power r is the same as e to the r times x. And because the derivative of e to the x is itself, the antiderivative or indefinite integral of e to the x is e to the x plus c. All right, so what I'm going to do now is basically do a bunch of derivative and integral problems involving the exponential function. All right, so go ahead and write down the question. The question is, find the derivative of e to the negative 4x times sine of 5x. Well, because we have two factors here. This is the first factor, and this is the sine 5x is the second factor. So we apply the we apply the product rule, which says that the derivative of f times s is equal to f prime times s plus f times s prime. Right? You take the derivative of the first. So when you have two factors, you're taking the derivative of a product of two factors. Then you take the derivative of the first factor multiplied by the second, plus the first factor multiplied by the derivative of the second. All right, so let's do this. So we get derivative of e to the negative 4x times the second factor sine 5x plus e to the negative 4x multiplied by the derivative of sine 5x, and which is then the derivative of e to the power negative 4x. What is that? Well, so if you look at e to the power negative 4x, right, that's the composition of e to the x and negative 4x. That is, e to the x is the outside of that composition and negative 4x is the inside. So the derivative of e to the negative 4x would be the derivative of the outside, which is e to the x, evaluated at inside negative 4x. So I get e to the negative 4x multiplied by the derivative of negative 4x, which is negative 4. So multiplied by sine 5x here, and then e to the negative 4x multiplied by the derivative of sine 5x, and the derivative of sine 5x is 5 times cosine 5x. Now, if you are not sure what I just said here, notice that the e to the power negative 4x means exp of negative 4x. So when you apply the chain rule, the derivative would be e to the exp of negative 4x multiplied by negative 4. So here is negative 4, and this is exp of negative 4x, written in this format. All right. So the way I'm going to simplify this derivative is I'm going to factor out e to the negative 4x because each term has that. So e to the negative 4x here. And then I have, if I factor this out, then I get negative 4 sine 5x here plus 5 cosine 5x. All right, so take a look at this and make sure that you understand how this works. All right, so here's another derivative problem. So we take the derivative of x times ln of x. So here the first factor is x, so the derivative of x is 1 multiplied by the second factor as it is, plus x, the first factor multiplied by the derivative of the second factor, and the derivative of ln of x is 1 over x. So what we get then is x times 1 over x, that's just 1, which I'm writing here, and 1 times ln of x is ln of x here. So I'm writing this term right here, and this is coming here. Okay, what's the derivative of e to the 1 over x? So I'm going to write that as exp of 1 over x. And so by the chain rule, this would be, by the chain rule, what's the derivative? Well, the derivative of the outside function is itself, right? So we get exp of 1 over x multiplied by the derivative of 1 over x. And the derivative of 1 over x is negative 1 over x squared. So then exp of 1 over x, I'm going to again write it as e to the power 1 over x multiplied by negative 1 over x squared. So again, the derivative of 1 over x is negative 1 over x squared. You can check that on your own. Okay, so what's the derivative of ln of absolute value of 2 minus x minus 5x squared? Well, recall that the derivative of ln of absolute value of x is 1 over x. So by the chain rule, I'm going to get 1 over 2 minus x minus 5x squared. then multiplied by the derivative of the inside function right here. So in other words, the function that I have here, that's the composition of ln of x and the ln of absolute x. Okay, I lost some of the text here. All right, so this is the ln of absolute x and 2 minus x minus 5x squared. So the function that we have is the composition of these two functions. So this being the inside, this is the outside, and the derivative of the outside is 1 over x, but then you replace x by the inside, which is what you get here, and then you multiply by the derivative of the inside, which is negative 1 minus 10x. Alright, so let's say I have y is equal to ln of 1 plus x squared. So then what is y prime? Again, by using chain rule, the derivative of the outside is 1 over x. So imagine that 1 plus x squared is just x, then the derivative would be 1 over 1 plus x squared. 1 plus x squared is not x, so you multiply by its derivative, which is 2x. So you get 2x over 1 plus x squared. Now, what's the second derivative of this function? Well, the second derivative is the derivative of the first derivative. So what do we do? Well, we apply the quotient rule to find the derivative of this. So we square the denominator, and then here the denominator, so multiplied by the derivative of the numerator, which is 2, minus the numerator 2x, multiplied by the derivative of the denominator, which is 2x. So, and if you simplify the numerator, you just simply get 2 minus 2x squared. All right, so here I want to find the inverse of the function f of x is equal to e to the x over 1 plus 2 e to the x. Well, to find the inverse, the first step is set y to the function. So set y to e to the x over 1 plus 2 e to the x. And then we are going to swap x and y. Okay, so I kind of did it a little bit differently. When I did it before, I didn't do the swapping yet. Let me just see for a second what I did. Okay, so basically what I'm trying to do here is I'm going to try to solve for x. And so set y to the function and then solve for x. Okay, so to solve for x, we are rewriting this equation. So y times 1 plus 2x, 2 e to the x would be equal to e to the x. Multiply out here, you get y, 2y e to the x, and then e to the x, send it to the left, you get negative e to the x is equal to 0. So now I'm going to send y to the other side, so you get 2y e to the x minus e to the x is equal to negative y. Okay, so I'm now multiplying both sides by a negative 1, so I get e to the x minus 2y to the x is equal to y. Factoring out e to the x here, so I get e to the x times 1 minus 2y is equal to y. Now e to the x is equal to y over 1 minus 2y, and e to the x is that, so ln, so now I apply ln function, so ln of e to the x would be ln of y over 1 minus 2y, and so therefore now I get ln of e to the x is just x, so I get x is equal to ln of 1 over 1 minus 2y, and so then finally f inverse of y would be ln of y over 1 minus 2y. So to find the inverse of this function, the idea is set y to the function and then solve for x. and once you solve for x, whatever you're getting in terms of y, that's f inverse of y. Now typically a lot of the times some people would do the following. They will set y to the function 1 plus 2 e to the x. They will swap x and y, so they will swap x and y, and then they will solve for y. And the only difference is that when you do that, you're gonna get, so when you do that, what you're gonna get is y is ln of x over 1 minus 2x. So you can compare what I have in red and what I have in black ink. So basically now I'm going to say this is the f inverse of x right here. And instead of that, I'm saying f inverse of y. So either way is okay. All right. So this is it. I think the rest of it are just a bunch of other examples. So this is all I need to say about the exponential function. All right, I will see you in the next video.